Hello, everybody, and welcome to our next unit in Unit 9, which is going to be all about electrochemistry. So electrochemistry, I think, is kind of exciting because it tells us how electrons move, actually. So let's get this definition down first before I talk a little bit more about it. But it's exciting because electrochemistry is the study of chemical processes that cause electrons to move, which is really cool. And if you think about what reactions have we talked about already that have caused electrons to move, what type of reaction from Unit 4 did we learn quite a bit about where there was electrons moving? We talked about those with redox reactions, actually. So electrochemistry deals with a lot of redox reactions because in redox reactions, of course, you have the reduction side of it, which is where it's a gain of electrons, whereas oxidation is when something loses those electrons. So we can take those particular reactions, and since electricity is a movement of electrons, we can study that, right? So how do electrons move, and how does that create electricity and voltage between two chemical systems? And what we can use to study this process is by using electrochemical cells. So an electrochemical cell, let's get the font stuff here that I like. An electrochemical cell is a system that either uses or generates an electric current. So all processes, not all, but a lot of processes will either, a lot of redox processes will either produce an electric current or they will use electric current. So a lot of things will either be thermodynamically favorable, and in that case, they will generate an electric current on their own. Or we have reactions that are not thermodynamically favorable, and we can force them to occur by applying electricity to a system. And we can name both of those two types. So whether we have a cell that either uses or generates electricity, it's going to be one of two types, and we could see those down here. So the first type is a voltaic or a galvanic cell. And a voltaic cell contains a thermodynamically favorable chemical reaction, okay? So this is going to really occur very readily, okay? If we think back to what we talked about, if something is thermodynamically favorable, its delta G, its Gibbs free energy, will be negative. So in this case, if something is thermodynamically favorable, it will produce a voltage, okay? So if something is thermodynamically favorable, which I have right here, we will have a positive value for voltage, okay? So in this case, voltaic or galvanic cells, they tend to be used interchangeably. These will generate electricity. And we're very familiar with voltaic and galvanic cells because we use them every day in our lives, okay? One way that we use, one example of these is a lead acid battery, and these are what we find in your car batteries, okay? You have very concentrated sulfuric acid in that battery, and you have some electrodes that are in there, and there's some redox reaction that's occurring, and that reaction produces a very large amount of electricity, which is then used to power your car in the most simple of terms that I can think of, okay? So that's one type of battery. These tend to be wet electrolytes. So this is where you have like your solution of sulfuric acid. On the other hand, we could also have dry cells, and these are very common in your handheld devices. Okay, so think about your cell phone, okay, or any type of battery you could buy from the store. Those batteries inside, they are not wet. They actually have a paste electrolyte. And if we had time, we could actually make batteries because it's pretty cool and it's actually quite simple to do. but we can make our own dry cell, and we use those all of the time whether you're working with some sort of electronic device. Anything that has a positive value for voltage or is thermodynamically favorable, that is in a voltaic or galvanic cell. On the other hand, we also have electrolytic cells. And our electrolytic cells is a non-spontaneous, except I'm going to write a thermodynamically unfavorable. So these reactions are not going to occur unless you input energy. Okay, so these are thermodynamically unfavorable or non-spontaneous reactions that can be forced to occur by the input of electrical energy. Best example I can think of, and I want to show this to you in class, is when we do the electrolysis of water. So I could take water molecules, and if you consider splitting water molecules into its elements, the decomposition of water, I have 2 hydrogen molecules and an oxygen molecule. If you think about redox reactions, okay, the oxidation number of elements are 0. So in this case, hydrogen is 0 and oxygen is 0. In water, oxygen is -2 and hydrogen is +1. Check this out. If hydrogen is going from +1 to 0, right, in this case, it is gaining 2 electrons, right? So hydrogen is getting reduced in this case. Oxygen, on the other hand, is losing 2 electrons. This is getting oxidized. So I have this transfer of electrons between these hydrogen atoms and these oxygen atoms. This process, however, the electrolysis of water, does not occur very readily. Water does not just split up into its elements without any sort of force to kind of provoke it to go. So we have to input energy to do this. And I will show you, I have these giant batteries in the room, and I will input some energy into water with an electrolyte in there so the electricity runs through. And we could separate water into its components in an electrolytic cell. Okay, I'm inputting electrical energy. However, you do have to know electrolytic cells. However, we're going to talk about the parts of a voltaic cell. And you could, I guess, use this for electrolytic cells too, but this is really important, this whole entire diagram right here. So what I'm going to do, I'm actually going to erase this so I make sure I have enough room. And let's go ahead and just label, what are the parts of a voltaic cell? So voltaic cells, remember, these guys will generate electricity. So they produce electricity. How do we know that they generate electricity? Well, because typically you're going to have some meter that's attached to this, okay? And this is a voltmeter. And this voltmeter is going to read how many volts are being produced in this system, okay? Because this is a voltaic cell, this would have to be a positive value, okay? You'll notice that I have 2 parts to a voltaic cell. This one thing is one whole system, one cell. However, I have 2 parts to this. We call those half cells, okay? So I'm going to use I'm not going to use this guy because it's going to be a little bit more writing. So let's just work right in here. But a half cell is where each of your half reactions take place. And of course, there's 1 in each half cell. So if we're considering that these reactions are movement of electrons and there are 2 half cells, okay, what types of reactions are occurring? Well, I'm going to have 1 half cell that has a reduction reaction, and the other half cell must have the oxidation reaction that's occurring, okay? So right here, this whole thing is our big voltaic cell. This whole side is 1 half cell. And this second side is also 1 half cell. Because of course a half makes a whole, right? Makes sense. What I also have in this system is I have this really important part, and that's this little thing going in here. We call this guy an electrode. And this guy on the same thing is the exact same thing. 2 electrodes. They have more specific names. We'll get into those in a minute or so. But let's get down what these electrodes are in this case. So, an electrode is an electrical conductor that's used to make contact with the non-metallic or the solution part of the circuit. Now, you do have 2 electrodes, but each electrode has a more specific name depending on what reaction is happening at each electrode. So you have an anode. The anode is the electrode where oxidation occurs. And you have your cathode, which is where your reduction occurs. So your anode and your cathode are the 2 specific names for the electrodes, okay? Oxidation always occurs at your anode, and reduction always occurs at the cathode. I literally always remember which one is which, because if I look, right, anode starts with a vowel, and so does oxidation. So oxidation occurs at the anode. And their cathode and reduction both start with not vowels, okay? So anode occurs at, or oxidation always occurs at the anode. That's literally how I remember it. I can't really label anode and cathode here because we're just drawing a very generic voltaic cell for now. So we'll label that in a little bit. The next part, what you have, so you have 2 half cells. And you'll see that both of these electrodes, and these electrodes are generally actual metal sheets. Okay, so it might be a big sheet of copper, a big sheet of, I don't know, silver, whatever it is. And you'll see that they're sitting in a solution. This solution is your electrolyte. Now, if you remember from a long time ago, electrolytes conduct electricity very well. Why? Because electrolytes have to have ions that exist in them. So I tend to have very soluble salts as electrolytes. And we'll talk more about what types of salts are best for specific voltaic cells. So your electrolytes, let's get a definition down for that, is the substance that contains free ions that behaves as an electrically conductive medium. So this is where your electricity is flowing through. It's either going into the electrolyte or it's going out of the electrolyte. And then I have one more very important part of this. So we'll see that this guy up here is actually our wire. So usually you could have some sort of a metallic wire, but you have a voltmeter that's attached to that. If you did physics, you probably remember circuits, right? So I have electricity flowing in some direction through the wire. However, we have to close this circuit, okay? So we have to make sure I have a constant loop that goes throughout. And that's what this guy right here in the middle does. This guy's called a salt bridge, and this salt bridge is super important. Let's get down what the definition of that salt bridge is. The salt bridge, let's go back up here and center it, is what connects the 2 half cells. It helps keep half cells neutral by allowing ions to flow between the 2 electrolytes. So if you think salt bridge, okay, your salt bridge is going to contain some solution of a salt, okay? A lot of times it'll contain something that's super soluble, like sodium nitrate, potassium nitrate, something along those lines. It has to have positive and negative ions, and those ions help to keep the reactions that are occurring in each half cell totally neutral. Okay, because your charge, remember when we were looking at buffers and when we look at all of these things, not only does the law of conservation of mass have to be satisfied, but your charges have to be balanced as well. And that's the purpose of the salt bridge, is not only to connect the two solutions to close a circuit. So I see here I have a totally complete circuit that goes around, but it's also to ensure that the charge and the electrolytes stay neutral. Without that salt bridge, the reaction would not happen. Let's go ahead and apply this to an actual reaction. So what does this look like? Okay, oops, let's go ahead and move this up a little bit. So let's be a little bit more specific at this point. So consider a voltaic cell that has zinc and copper electrodes, and my electrolytes are zinc sulfate and copper 2 sulfate. Okay, we want to know what voltage is produced. As we progress through this unit, we're going to find that we are given standard reduction potentials, and that reduction part is important because you are always going to be given the amount of electricity that is either required or is produced when that particular ion gets reduced. Okay, so again, reduction is a gain of electrons, so it's gaining electrons. If I look at the zinc ion, and when that gains 2 electrons, so when this gets reduced to produce metallic zinc, this process requires energy. Okay, we would have to input 0.76 volts of electricity in order to reduce zinc. On the other hand, if we want to reduce copper, copper reduces a lot more easily, actually. So much so, it actually produces electricity when copper gets reduced. So I have one process that requires energy, and the second process, or requires electricity, and the second process that produces electricity. Now, when we consider a voltaic cell, we're not going to have 2 reduction reactions occur. I can't have zinc ions and copper ions both losing electrons. That can't happen. The electrons have to go somewhere. So one of these reactions has to get oxidized. The question is which one? In a voltaic cell, remember, voltaic cells, these guys have a positive voltage. They produce electricity. They generate electricity. So if these generate electricity, okay, which one of these reactions would have to be oxidized to give me a positive value for voltage? Well, it would have to be the oxidation of zinc. Because if I flip this reaction to oxidize zinc, so look right here, I flipped that first reaction, and just like we've been doing, Gibbs free energy, entropy, enthalpy, right? When you flip that reaction, it changes the sign of whatever you're dealing with, okay? Except equilibrium constants, they're a little bit different. You don't just flip the sign there. I think it's 1 over, okay? In this case, it's going to make it a positive voltage. So now we have an oxidation and a reduction reaction because look, when zinc is getting oxidized and when copper is getting reduced, that produces a positive value for voltage. And this is what we call the standard cell potential, okay? Standard cell potential. Notice here, just like with Hess's law, your number of electrons have to cancel. So I have 2 electrons in the products in my oxidation, and I have 2 electrons in the reactants of my reduction. That gives me the overall net equation that's below. So zinc reacts with the copper ions. They switch some electrons around, and I produce zinc ions and metallic copper. And that process produces a voltage of 1.10 volts. And the higher the voltage, the more work the reaction can do, which makes sense. If I had 5 volts that's produced, 5 volts could power something a lot better than 1 volt can, okay? So makes sense. The higher the voltage, the more work the reaction can do. Let's look at this guy right here. So what we're going to do is we're going to draw the components of the voltaic cell using this reaction that was listed. And a lot of that information is given in this first section right here. I'm going to draw, and it doesn't matter what side you do them in, I'm going to make this electrode my zinc electrode. So this is solid zinc, a literal piece of zinc metal. And I have my copper metal. So a literal piece of copper metal. Both of these are my electrodes, okay? The zinc metal must be submerged in the zinc electrolyte, which is ZnSO4. Aqueous. Now this particular solution is very soluble in water. So in this aqueous solution, I'm going to have zinc ions floating around, and I'm going to have some sulfate ions floating around. Without those, we can't have electricity, okay, because we need an electrolyte to do that. On this side, however, I have a copper 2 sulfate solution. Same thing here. Copper 2 sulfate is very soluble. So I have copper 2 ions and I have some sulfate ions floating around in that solution. If we look back at this reaction here, so we already established that in this voltaic cell, your zinc is getting oxidized. Okay, so this must be the oxidation where oxidation is occurring. And reduction is occurring here. If we consider what's the specific name for each of these electrodes, yes, it's an electrode, but your reduction is going to occur at the cathode, and oxidation is going to occur at the anode. Let's go ahead and just write the reactions that are occurring down here. So in this reduction side, I have 2 electrons are combining with copper ions to produce metallic copper. And zinc metal is oxidizing to make zinc ions and 2 electrons. So we also have already established that we have a voltmeter up here. So there's some sort of thing that'll read the voltage, and we already established it's 1.10 volts. Where is the flow of electrons going? Okay. If zinc is being oxidized, this metallic zinc, this solid zinc, that means that this solid zinc is losing 2 electrons. And where are those electrons going? They are flowing to the cathode. Why? Because copper is getting reduced. Copper has to gain those 2 electrons. So the electrons are going to flow in this direction from zinc to copper. Copper is going to get those 2 electrodes. Okay. What happens? So if this zinc, if this metallic zinc, this anode, if that is losing electrons, okay, what's going to happen to this zinc? This zinc is going to start to disintegrate, right? This metallic zinc is going to break down. So literally we will see this electrode start to disappear. And what's going to happen to this? All of that metallic zinc becomes zinc ions in the solution. So I'm going to produce more zinc as this reaction occurs, because that metallic zinc is going to form zinc that's dissolved in the solution, the electrolyte. And they come over here, right? And copper is going to gain those electrons. Now, this copper is already maxed out, right? It already has its 2 electrons. These copper plus 2 ions are gaining those electrons. And where are those located? In the solution. So these copper plus 2 ions actually go onto the electrode, and this electrode is going to get bigger. We're going to see some metallic copper start to precipitate on the top of this substance, okay? And what we're going to see here is that this solution is going to become more negative, because if we're taking those copper ions out, those positively charged copper ions, I'm going to have a larger concentration of sulfate that's left. And this is where the salt bridge comes in, is because I have a lot of positive ions here and I have a lot of negative ions here. I can't have that. The charge has to be neutral. So let's say I have my salt bridge, and we're going to say the salt bridge is just made up of sodium nitrate. In this direction, okay, in my half cell that has the oxidation, I have a very large percentage of positively charged ions. So my nitrate from that salt bridge is going to travel into this beaker to help neutralize the charge. On the other hand, if my copper is going into this and getting reduced and I have a large concentration of sulfate, this means that my sodium ions are going to move in that direction. I need positive ions to go towards that side, okay? This is exactly how a voltaic cell works. There's a lot of stuff that's occurring, okay? And it's actually quite interesting. It's a really cool process. I don't know why there's like so many dots on this page, and maybe this pad I have is kicking the bucket. I don't know. But yeah, it's really neat how this occurs, and hopefully we could do a quick example in class for you to see this, because you can make batteries just out of solutions, a little YouTube with some salt water in it, and works great. And that's it. So every voltaic cell will have this type of setup. Let's go ahead and just try the next 3 sample problems, and these should be pretty quick. But I want you to see some examples here. What in the world? So let's try these 3 sample problems very quickly, and we're going to see this is a very simple process, okay? So, is the reaction below favorable? Looks like I have zinc ions reacting with iron plus 2 ions, and I'm producing zinc metal and iron plus 3 ions. You might have a standard reduction potential chart. I will email this to you too if you have it, but you can look up these standard reduction potentials, and we can look up, okay, so what is the reduction potential in this case from zinc plus 2 to zinc? And what is the reduction potential going from either iron plus 2 or to iron plus 3 to the opposite, okay? And if we look on that chart, here's what we'll see. That I have Zn plus 2. And that is going to combine with 2 electrons. And I'm going to produce zinc metal. That's the reduction potential. And in that case, I am producing negative 0.76 volts of energy. On the other hand, if you look at that standard reduction potential, we'll find, I don't know why this pad just keeps making dots everywhere. I am not pressing everything, so I apologize if this is going to look very sloppy towards the end. I don't know what's going on with this computer or this pad. I'm going to restart it after I finish this video. Look at that. What in the world is happening? But I look on that chart and I find that 2 Fe plus 2 gets oxidized actually in this reaction and produces Fe plus 3 and 2 electrons. Now on your standard reduction potential sheet, what it's listing is it says I have Fe plus 3, and that's combining with 1 electron to produce Fe plus 2. And that's telling me that that process is positive 0.77 volts. Positive. When I flip this, okay, the voltage is going to become negative 0.77 volts. However, we do not have to double anything. We don't have to do anything to that voltage, even though I have doubled all of the coefficients in this reaction to get the electrons to cancel. The voltage is going to stay the same. What is going to change if there are more moles of that present is that this will produce electricity for a longer period of time. The amount of voltage is not increased or decreased. So you do not have, and I repeat, you do not have to multiply any voltage by any value like you did with enthalpies and entropies and all of that. When I add these together, I get a value of negative 1.53 volts. And the question is asking is this favorable? The answer is no. This would be an example. If this reaction were to occur, this would have to occur in an electrolytic cell. I would have to input 1.53 volts of energy in order for this reaction to occur. And that is not going to happen in a galvanic cell because galvanic cells produce electricity. All right, so I did restart my computer because that was really driving me crazy, that last one. So hopefully we fix the issue here, but I guess we'll find out very shortly if it's not fixed. Let's calculate the standard cell potential. So this is another way of saying the voltage. We want to calculate the voltage for this reaction. First, what we'll do is we'll look up the standard reduction potentials on that green paper that you have. So if I look, I have iron +3 to iron +2. And actually, I think we have that one above, if I'm recalling correctly. And if I look at the chart, it actually is getting reduced. So +3 to +2 is reduction. I could keep this reaction exactly the same. So I have Fe +3. Looks like it's already working better. Plus 1 electron is going to give me Fe +2. And that has a positive 0.77 voltage right there. Let's look up copper to copper +2. Now, in this case, copper is getting oxidized. So I will need to find the reduction of copper +2 on this green paper. So copper +2 getting oxidized to just regular copper with an oxidation of 0. You do have to be careful. Looks like I would have to flip it. So Cu is getting oxidized to produce copper +2. And 2 electrons. This process produces 0.34 volts of electricity. The only thing is that, or the reduction produces 0.34 volts, but I did oxidize it, so we are going to just switch that value right there. These electrons don't cancel out, so actually to properly balance this, I do have to multiply everything in this first equation by 2. So I would have 2 Fe +3s, 2 electrons, and 2 Fe +2s. But remember, I don't have to change the sign for the voltage. The voltage will be the same. The only thing is that if you increase the amount, you can produce the voltage for a longer period of time. So if I write this balanced chemical equation, because if I look, this is not balanced. My charges are not balanced. I have +3 on this side total and +4 on this side total. When I do this part, this should balance the reaction out. Fe +3, 2 Fe +3s reacts with 1 copper. And I produce copper +2 and 2, Fe +2s. So if I look, 2 plus 4 total gives me a charge of +6 total. 2 groups of +3 also gives me +6. This equation is now balanced. And my voltage here, my E's naught, or my standard cell potential, would be 0.43 volts. So that equals E naught, standard cell potential, positive. Not a very good galvanic cell because it's not producing that much voltage. Let's take a look at sample problem 15. Oh boy. So I have this galvanic cell is based on the reaction below right here. And here's 2 half reactions. We want to give the balanced cell reaction, and we're going to calculate E naught for the cell, okay, the standard cell potential. Looks like we're going to have to use some Hess's law right here. So I have permanganate as a reactant. I have permanganate as a reactant here. So I'm going to leave that first reaction. MnO4 - 1 plus 5 electrons plus 8 protons yields manganese ions and 4 waters. I didn't switch that reaction, so I'm going to keep the voltage positive there. Looks like I do have to switch this second reaction. So I do have ClO3 on the reactant side, and here it's on the product side. So I'm going to flip this reaction around. ClO3 minus 1 plus a water molecule yields ClO4 minus 1, 2 protons, and 2 electrons. Remember, just got to change the sign for the voltage. So I can, in fact, calculate the standard cell potential. That is 0.32 volts positive. However, the second part of this is asking us for the balanced cell reaction. So we do have to consider, okay, well, what do I have to do to get the electrons to cancel? Okay, remember, I can't just have electrons floating around in the solution. So I'm going to multiply this first reaction by 2 and this second reaction by 5. So I have 10 electrons total on both sides. I'm going to spare you the whole entire long thing because I know you know how to do this. I'm just going to give you the final equation for you to check yourself. So you have 2 permanganates, 6 protons, 5 ClO3 minus 1 yields 2 manganese ions, 3 water molecules, and 5 ClO4 minus 1. There should be a plus. I don't know why that positive is so far down. It should be up there. And here's our balanced equation. Okay, balanced equation and the standard cell potential, which works. I think these calculations for standard cell potential are quite easy. The only thing you got to remember is you can't multiply those voltages, right? If you flip it, you change the sign, but otherwise that's it. They stay the way that they are. We have one more video to wrap up this unit. So excited because then we're done. Woo! And that video will be on relating that cell potential to free energy. And we'll just talk a little bit more about voltage and what that does to voltage if we change concentrations of stuff. As always, if you have any questions, let me know. Otherwise, I will see you in the next video, the last video. Have a wonderful day. Bye.